Hello, good afternoon, and welcome to this webinar titled Electromagnetic Modeling with EMS for SolidWorks, a quick walkthrough. My name is Arvind Krishnan, and I will be your presenter today. On behalf of EMWorks, I would like to thank you all for attending today's webinar. Before I start, just a few bookkeeping items for today's presentation. First of all, a recording of this webinar will be done and sent to you by tomorrow. So you are free to share this webinar with the rest of your colleagues who are not able to come today. Second, towards the end of this webinar, I will be happy to answer some of the questions you may have had during this presentation. If you have some questions for me, kindly use the chat window of the GoToMeeting. Please type in your questions, and towards the end of the webinar, I'll try my best and answer the questions. With this, I would begin the webinar, and as a courtesy, I would request all the participants to mute their microphones during this presentation. Thank you, and let's begin. I'm going to start with the company. We're going to talk about the company EMWorks. It was founded in 2000. We are located in Montreal, Canada, and we offer electromagnetic simulation software for SolidWorks. As of 2008, EMWorks products are gold certified products of SolidWorks. And in today's webinar, we're going to see one such flagship product called EMS for SolidWorks. Now, really, what is our vision? Our vision is to empower SolidWorks users to use the best electromagnetic simulation tools out there for SolidWorks environment so that they can do their designs on the computer without a need for prototyping and come up with the most optimal design before and validate the design before they can embark on getting started with product manufacturing. And why must one choose EMWorks? It's basically because it's completely embedded inside SolidWorks and it's a single engineering platform. And also, this obviates the need to export geometries from one CAD package to another simulation environment to run the simulation. Now, let us talk about the product that we will see today. It's called EMS for SolidWorks. It's the electric and magnetic 3D field simulation software. Okay, it's got both electric solvers as well as magnetic solvers. The electric solvers are electrostatic, electric conduction, AC electric. The magnetic solvers are magnetostatic, AC, and transient magnetic. EMWorks also offer a few add-on products or add-on solvers as they can be called. We can do thermal analysis, motion analysis, thermal stress, and also circuit analysis. And these act as add-ons. The next product is HFWorks, which is a high frequency simulation software. Of course, it is not the topic for today, but HFWorks has the capability to do S parameters, antennas, resonance, and time domain reflectometer. It also has add-ons in the form of thermal stress, and power handling capability. Over the years, a lot of companies have added EMWorks into their product development environment. And here are some of a few of the companies that utilize our product as of today. Not just in the industry, but also EMS for SolidWorks is well known in academia. and a lot of leading universities all around the world are proud to use EMWorks in their day-to-day teaching and research environment. And they range across various application areas from aerospace, defense, manufacturing, energy, electronics, healthcare, and so on. So EMWorks products find a wide range of application across multiple industries. Now here is a slide that kind of encompasses all potential applications of EMS. So you can see from electromechanical to electromagnetic, power electronics, EM behavior is tackled under the product EMS for SolidWorks, and high frequency RF microwave design, signal and power integrity is tackled using HFWorks. Now we will be discussing several applications of EMS, and I will actually go over some of them before we show a demonstration of the product. So the first thing that I would like to show is the AC heating of a tooltip, which is used for plastic welding. Now this makes use of AC magnetic simulation. So, and the objective is to compute the temperature distribution due to the AC currents going through the plastic welding tooltip. Now EMS will be able to accurately predict the temperature of the tip, and you will also be able to study how the temperature varies with respect to the value of the AC current that is passed through the tooltip. The next kind of application, now I'm just giving you a suite of applications that are possible. It certainly doesn't encompass all the applications, so we're going to study a few of them in this presentation, and after that I will show you a couple of demonstrations, a live demonstration of our product. The next is magnetic bearing designs. Now this uses just permanent magnets, and we use the magnetostatic simulation to perform this simulation. Now this predicts the force acting on the inner bearing as a function of its axial position. As you can see in the graph, EMS can be used to predict accurately the force acting on the inner bearing as it varies its position along the axis. EMS can be used to do multiphysics problem wherein electromagnetics and motion can be used together to simulate and study the movement of electromechanical devices, like for example a solenoid. In this particular example, EMS transient simulation along with motion is used to predict the forces and the position of solenoid as a function of time. Now this uses both SolidWorks motion as well as EMS to do the job. Now another type of example is the rotational magnetic circuit. In this particular example, EMS was used to compute the inductance calculation for a magnetic circuit by using a magnetostatic simulation. Next, EMS can be used to study a wide variety of permanent magnets. For example, a cylindrical Halbach array or a linear Halbach array. So in this particular image that you see, a cylindrical Halbach array, a ring of several magnets positioned as shown, can be used to understand and visualize the magnetic flux density and the forces due to this arrangement. And in this particular example, the magnetostatic simulation of EMS was used. EMS can be used to study motors and generators and its performance. Now, a transient magnetic simulation with coupling to motion, SolidWorks motion, was used to study the performance of this permanent magnet generator. EMS is also used in the transformer industry to study and understand the behavior of transformers, especially with respect to the temperature that is generated as the transformer functions. Now, this can be used to devise an efficient cooling strategy for the transformer. And EMS can be used to compute the maximum temperature that is attained in the steel enclosure of the transformer or the bus bars that carry the current to the transformer. In this particular example, the AC magnetic simulation was utilized. Then sensors. EMS is widely used in the world of sensors, exploiting electromagnetics. In this case, a high-speed rotational speed sensor can be simulated for its efficacy using EMS transient magnetic simulation coupled with motion. For example, the EMS computes the back EMF on a coil due to the rotation of the gear wheel, and this back EMF as a function of time can predict the speed with which the wheel is rotating. Finally, the electrostatic module of EMS can be used to compute capacitances. For example, this is a MEMS capacitor, and EMS can be used to compute the capacitance of complex capacitors, as one can see there. So with this slide, I'm kind of covered some basic applications that EMS for SolidWorks can handle. Now, I will be showing you a couple of demonstrations using the product, and this will help you to understand the workflow of EMS for SolidWorks and also understand the various pre and post processing features available in the software. So without further ado, let me show my SolidWorks, and the first example that I will be showing you is that of a rotational actuator. Now, as you can see here, this is a rotational actuator that was created using SolidWorks CAD. The objective of this magnetostatic simulation would be to compute the the torque acting on the rotating inner core, as you see here highlighted in blue, due to the excitation of the coils in this magnetic circuit. Now we will be applying a particular excitation of the coils, and we would be computing the torque acting on the inner rotational core. Let us see how EMS will help us do this problem. First of all, as you build your geometry in SolidWorks, EMS is an add-in product that can be accessed right inside SolidWorks. Now, when I click the EMS tab, we are ready to perform the simulation. The first step in doing a simulation is to create what is called as a study. So I can create a study. Here are the 6 different study types that I mentioned to you earlier. We'll go over them. When you have electromagnets with DC currents or permanent magnets, you would use what is called as a magnetostatic simulation. When you have AC currents, you would use AC magnetic simulation. Or when you have a combination of AC, permanent magnets, and DC current, and you want to study a time varying phenomena, then you would use transient magnetic simulation. These 3 cover the magnetic solvers in the product. Now, one can use or exploit parametrization, wherein any simulation parameters like current, etc., or any geometric parameters like the diameter, length, and so on can be parameterized, and one can study how a geometry parameter or a simulation parameter affects the electromagnetic results. And if you browse through our web page, we have webinars talking about specific parts of the software, and we also have a webinar talking about how parameterization is realized using EMS. Okay, so as far as coupling goes, we have the ability to couple to thermal stress, structural, and motion coupling. In this particular example, we will not couple. So when you create a study, EMS creates what is called as a study tree. Now in this particular study tree, we will define the material for the various geometry. Now for example, the coils, as I highlight here, are made of copper. So to define the material, I can use the EMS material library that comes free with the software and which is completely customizable. Now EMS materials are categorized and they are conveniently arranged for you to apply. For example, you can, from the conductor material, you can choose some conductors, in this case copper, and use it to apply to the bodies that are made of copper. The inner and the outer core are obviously magnetic materials and they are made of 1010 steel. So again, one can look into the steels that are available, and EMS brings you all the electrical and magnetic properties of your material. And as I mentioned earlier, this material library is completely customizable, which means you can create your own material, input the data, and use it for your simulation. Now, there are two other things that are important for electromagnetic simulation. It's really the air geometry. Now, any EMS simulation requires you to create the air geometry inside SolidWorks, and that's simply a part that covers the geometry as you see here. And then we use a cavity option in SolidWorks. It's a part option where you subtract all the other components so that you can form the air geometry. Now we have videos explaining how this is done, so I will not go over it, but essentially any EMS simulation requires you to create what is called as the air geometry. I'm going to go ahead and hide the air geometry, and now let's see the next step. The next step is really to create the coils. Now EMS has a very nice and elegant way of defining coils. To define a coil, one needs to select the component or components that comprise the coil. We need to select the cross-section face through which the conductors or the current flows. Then we go to the properties. Here is where we will specify the wire gauge of the wire that is used to wind the coil. We specify the number of conductors that pass through this cross-section, in this case 200, and finally we specify the current through each of these conductors. In this case, it's 2.1 amps. Similarly, the second coil is also defined with almost the same parameters, except that the geometry comprising the second coil is different. The cross-section face is shown here. The wire gauge, the number of turns, and the current is all the same as in the case of the previous coil. Now, once the coils are defined, we would like EMS to compute the torque acting on the inner rotor core. Now, this computation is done via a method called virtual work method, and hence I'm using EMS to define a virtual work on the inner rotating core. Once the simulation is complete, we will take a look at the results. Okay. Now, the second important thing, I mentioned two important things to do in EMS simulation. One is the air geometry, and the second one is the concept of finite element mesh. We use a technique called finite element analysis to do this, to solve the electromagnetic equations, and hence it's very important to discretize or break up this problem into small finite elements, and that is then automatically using EMS meshing feature. Now, there are some mesh controls options that are available for you to control the meshing. As you can see here, we have applied a fine mesh on the inner rotating core, whereas we have applied a coarse mesh on the outer rotating core. So one can exploit these mesh control options to refine the mesh selectively on important geometry so that you can get accurate results. Now, I have run this simulation prior to this webinar, so we will delve quickly into the results. EMS can generate two kinds of results. One is the qualitative results, whereby one can get a distribution of the magnetic flux density, locate and identify regions of high flux, and so on. The second is quantitative results. We will start with that, and that is available in what we call as the result table. So if I double click the result table, I can actually study the torque acting on the rotational actuator. So the torque, the predominantly is acting about the z-axis of SolidWorks. So the torque acting about the z-axis can be found out from here. So EMS automatically computes the torque acting on this rotational actuator about the z-axis. Next, we will take a look at the qualitative results. Now, this is a plot showing the magnetic flux density in the whole magnetic circuit, and it can help you to identify areas of high magnetic flux in Tesla. So you can study how the magnetic flux density is distributed in the model. So oftentimes one would like to look inside the model. So we have a feature called section plot that helps users to look at the magnetic flux density through any cross section of the model. Now here I've just taken the XY plane and I've cut the model so that I can look at the magnetic flux density inside my model. So the section plot feature of EMS helps you to go inside your designs to understand the qualitative aspect of it. Okay. Now, basically, this small demonstration helped you to understand from A to Z how a simulation can be set up right from your CAD geometry all the way to looking at the results. Now let me go ahead and close this model so that I can now turn my attention onto another problem. Now this problem is a linear Halbach array, which has a series of permanent magnets that are brought together to form this array. Now the north-south directions are smartly determined of these permanent magnets so that it creates what is called as an Halbach array, whereby the magnetic field in the bottom portion of this array is much stronger compared to the magnetic field on the top portion of this magnetic array. So let us understand how EMS can be used to study the distribution of magnetic field around this array of permanent magnets. Again, we have created this model in SolidWorks. I've also created the air geometry in SolidWorks. As I mentioned earlier, it is absolutely necessary to create an air geometry to do any EMS simulation. Now, as before, we will go to the EMS Manager tab where we have created a magnetostatic study, as you see here, and I have defined the material for the various magnets. For example, each of these magnetic tubes are made of neodymium N42 material. Now, once the material has been defined, we will also have to define the direction for the magnet. So for example, one of the directions, as you see the second magnet here, which is highlighted in blue, is along the negative x-axis. So one can define direction of the magnet either using a global coordinate system or a local coordinate system in SolidWorks. And you can use the three commonly used Cartesian, cylindrical, and spherical coordinate system to define the direction. This way, I am able to define the directions of each of the magnets, which are also highlighted using arrows for our convenience. So you can see how the magnets are arranged in this Halbach array. Now, once the problem is defined, as before, we require a finite element mesh, which has been automatically created, and we ran this problem prior to this webinar. So let's go ahead and take a look at some of the results. The first result that I would like to show is the magnetic flux density, a section plot through the Halbach array. As you can see here, the flux or the field strength in the bottom is much higher than the field strength in the top. So qualitatively, we can understand what happens in a Halbach array. And you can also measure the value of the strength because you're able to read from the chart these values, the light blue areas and the dark blue areas. But oftentimes, we would like to precisely understand what is the value of the magnetic flux. For example, I have drawn a line here which is at a particular distance from the bottom of the magnet. And maybe it is my intention to know what is the distribution of the magnetic flux along this line. So I can accomplish this by creating what is called as a 2D plot. Here I have selected the two endpoints of the line segment, and I have requested the program to compute the distribution of the magnetic flux density from say point 1 to point 2. Now this can help me to visualize how my flux density varies at the bottom of my Halbach array from point 1 to point 2. Now I can actually go ahead and look at these values, and I can even export them out into Excel or a text format. This helps me to really understand the distribution of flux anywhere inside the air domain or inside any physical geometry, and understand how the magnetic flux distribution happens in that particular line segment. This is called the 2D plot. Hence, we have seen two basic examples, one of a rotational actuator to compute the torque, and other is a series of magnets to compute the magnetic flux density at a particular location from the bottom of the magnet. And we have also seen some tools like the section plot, etc., to study the qualitative aspects of your results. Now, with these two short demonstrations, I would actually want to revert back to my presentation slide, where I would like to conclude this particular webinar. Now, just as a recap, we saw EMS and its functionality. We also did a quick tour of the EMS product, whereby I showed you a couple of demonstrations. You looked at the seamless integration between CAD and simulation inside the SolidWorks environment. And we also saw a plethora of post-processing, result processing options available in EMS for SolidWorks. With this, I would like to thank you all for taking the time to attend today's demonstration. As I said earlier, we have recorded this demonstration and we would like to send you a link to this webinar. Now, for more information, please visit our website, emworks.com. We have white papers, customer testimonials. We also have a link to our YouTube channel from our website, whereby you can access hundreds of different applications that have been simulated using EMS. If you have any questions regarding sales, our number and the email address is mentioned. And finally, I would like to let you know that you are welcome to use our website and enter in your information to download a 15-day free trial of the EMS product. With this, if there are any further questions, I will be happy to take them and answer them. So please use the chat window to type in your questions. Okay, if there are no further questions, thank you very much. And I hope to see you again on another webinar. And if you wish to have any further communication with us, our details are given in the slide, and we look forward to hearing from you. Thank you. And on behalf of EMWorks, have a nice day. And thanks for attending this webinar. We will close this webinar right now.